So today we already learned the rational root theorem. That was yesterday. Today we're learning the irrational root theorem, which uses conjugates. So conjugates are number pairs in the form a plus the square root of b and a minus the square root of b. Example using numbers. You'll see conjugates a lot in pre-calc and calc, even in, if any of you take Oracle with Ms. Cotton, she uses conjugates in some of her programming. Although it may be more coding conjugates than it is algebra. But if you know one of these is an answer, a root, you'll know that the other one is. Why? Maren? The plus or minus. Normally our answers come out to be 2 plus or minus the square root of 3, right? Technically that's two answers. That's 2 plus the square root of 3 and that's 2 minus the square root of 3. That's basically what the irrational root theorem says. It tells you if you know that an irrational pair of numbers is a root or a 0, then you'll know its conjugate also has to be a 0, because if you have something plus the square root, then the minus has to be there as well from our quadratic formula. So that's what this theorem says in layman's term. If you know a plus the square root of b is a root, and it has to have rational coefficients, so that's also important, I guess, to mention, meaning that the coefficients of the original equation have to be fractions. So like 1/2 x cubed plus 2x squared plus 3x plus 1. So all of the coefficients have to be rational, being able to be written as a fraction. Then you would know a minus the square root of b is also a root. Examples below ask us, if we know these are roots, find two additional roots. So if 2 minus the square root of 5 is a root, then its conjugate, 2 plus the square root of 5, is a root. Now, the square root of 7 isn't in the form a plus. It's really 0 plus square root of 7. You don't have to write it like that. But so its conjugate would be negative square root of 7. Switch the numbers around. But yes. So we would have 2 plus the square root of 7, its conjugate, and negative square root of 5. Before we move on, if you were to know that these are the roots of the equation, what would the degree of the polynomial be? Would it be a quadratic, a cubic, a quartic, a quintic? Maren? Quartic. If we know these are the only ones. 1, 2, 3, 4. 4 zeros must be a 4th degree polynomial, meaning therefore it must be quartic. I feel like that comes up at some point, maybe in a homework question. Alright, the next one says one of the roots of the polynomial is 4 minus the square root of 2. Doing the same thing again. Can you be certain that 4 plus the square root of 2 also is a root?
Yes.
No.
Pretty certain. Pretty certain.
Go back up to our theorem. What did I underline? Rational coefficients. So if you notice in these examples, they told us that it has rational coefficients. It has rational coefficients. This one does not tell us that it has rational coefficients. So technically you don't know for sure. Because they don't give you the equation to be able to look at it and know that they're rational, and it also doesn't tell you. So you just have to be careful with that. All right, next vocabulary word is, instead of just a conjugate, it's a complex conjugate. So complex numbers were our imaginary numbers, like 2 plus 3i. So these would be numbered pairs in the form a plus bi and a minus bi. It's kind of the same thing as above. Whenever you get a answer using the quadratic formula, like 2 plus or minus I square roots of 3 over 3. Right? You get two answers. One is a positive, one is a negative. Those are considered conjugates. Notice that you do not negate the front of the term, it's just the symbol in between, the plus or minus. So the imaginary root theorem says if an imaginary number, a plus bi, is a root of a polynomial equation, this time it says they have to be real coefficients, which means they could be rational or irrational. They could be square roots, or they could be numbers. Then the conjugate a minus b is also a root. So, polynomial equation with real coefficients, so check, that's good. Has roots 2 plus 9i and 7i. What would our two additional roots be? Lucy?
2 minus 3i.
And? Good. Here's the degree question. I knew it was coming. If a polynomial with real coefficients has 3i and negative 2 plus I among its roots, then what two other roots must it have, and describe the degree of the equation. So what would my two other roots be? Negative 3i. Be careful with the second one.
2 plus 2 minus
Negative 2 minus I. You do not change the symbol in the front. It's only the plus or minus in the middle. That's one place also you guys made mistakes. And then this will be the same as the one I went over already. Describe the degree of the polynomial. We have 4. It's a fourth degree, which we would call quartic. Now what we're going to do on the back is we're going to skip number 10, because it's basically the same thing. Number 11, 12, and 13 are all the same types of problems. So if I get through one, we should be able to understand them all, but we'll see. Oh, do you not have a 10 on here? Oh, 10 was on the front. I'm sorry, it was on my back. Okay, I must have shrunk that up. All right, 11. Find a third degree polynomial equation. So it has to have an equal sign. Remember, some of us lost our half point the last quiz. Forgot the y equals 0, f of x equal sign. With rational coefficients that has roots negative 2 and 2 minus I. So using the complex conjugate, we know if 2 minus I is a root, then we know also 2 plus I is a root, the imaginary root theorem. Does that also mean that positive 2 is a root? No, because it's not a conjugate. It's not in the form a plus the square root of b, a minus the square root of b, or a plus bi, a minus bi. So, and they also tell you it's third degree. So, you have three roots. You have x equals negative 2. You have x equals 2 minus I. And you have x equals 2 plus I. And it probably should have also said in here that I want it in standard form. So if you remember in our last quiz, there were some like this, where I told you the three roots and asked you to write an equation. So what you're going to do is you're going to work backwards to get these into parenthesis forms and set equal to 0. Using inverse operations. So I'll add 2 to both sides. I'll get x plus 2. That's going to be one of my factors that I'm going to FOIL. Now to move this around, you have to subtract 2 and add I. Be really careful that your eyes don't look like 1. And then on the second one, we would subtract 2 and subtract I. So now what we're going to do is we're going to take all three of these, put them together, and then we're going to have to do a bunch of FOILing. Now, after we do it the first time, some of you will notice a pattern, like a shortcut, that will possibly, if you remember the shortcut, save you time from having to FOIL everything. My suggestion would be to FOIL, I think, these two first. And then we'll distribute the x plus 2 at the end. Now, when I say FOIL, it's really going to be more than FOIL, right? Because we have 3 things distributing to 3 things. So, x times x squared. X times a negative 2, minus 2x. X times a negative I is a minus xi. Bless you. So take the first term, distribute it to all 3. Now, move to the second term, which is a negative 2. Distribute it to everything. So negative 2 times x is a minus 2x. Negative 2 times a negative 2 is a positive 4. And negative 2 times a negative I is a positive 2i. But wait, there's more. Now I have to distribute the I. It's like an infomercial. Keeps going. So I times x, and again, you may want to write this as the same way that you wrote the other one. Instead of ix, write xi, so that you realize they're like terms. I times a negative 2 will be minus 2i.
Please excuse this interruption. Students, Saturday detention. Anybody who needs to serve Saturday detention, please enter the building through the main front doors and proceed to room 172 for your detention. Again, enter the building in the main front doors, proceed to room 172 to serve your detention. Thank you.
Thank you. All right, last term. What do I get when I multiply I times negative I? Negative I squared. Do we remember what I squared is? I squared equals a negative 1. So when you plug that in, it's really minus a negative 1, which is then a plus 1. Because it was a minus I squared. I squared is negative 1. Minus negative gets me a plus 1. So now let's go ahead and cancel out whatever we can, because there should be some stuff that cancels out. We have a minus xi and a plus xi. We have a plus 2i and a minus 2i. And everything else should stay there. But we have to combine our like terms. So I have minus 2x, which is a minus 4x. I also have plus 4 plus 1, which will get me plus 5. So basically when you FOIL these, every time, you're going to get x squared minus whatever the terms obviously are. So 2 and 2 gets me my minus 4x. And then 2 times 2 would get you 4, but then you're always going to add 1 because of the I squared, minus an I squared, which will just get you 5. And you'll see that when we do the next one. So some of you will pick up on that and you won't actually do this work. You'll just notice the pattern and continue it. But that's why the pattern would work, because they end up being conjugates, which has a lot of stuff canceling. Kind of like our x plus 2, x minus 2, if you were to FOIL it, things cancel. Those are conjugates. Now the last step is to FOIL again. I'm running out of space, so let me just cover this up with a text box. For board purposes, sorry you don't have the same luxury. So we'll get x cubed minus 4x squared plus 5x, distributing your x to each term. Then distribute your 2. Make sure you have equals 0. I'd also accept y equals, but technically since it says an equation and not a function, it should be equals 0, since they gave us the zeros. And then last but not least, combine your like terms. And we should get x cubed minus 2x squared minus 3x plus 10 equals 0. Unfortunately, there's no way to put this in your calculator and do like a cubic regression because it has the imaginary roots. Your calculator only deals with real solutions. So the bell's going to ring in about 3 minutes. why don't we move down and do 13, because some of you may have run out of space anyways. 12 was kind of similar. 13 is actually a little bit easier because it doesn't have the 2 minus I, so that's going to be shorter. And some of your homework questions will be like this. So this time they tell us to find a 4th degree polynomial equation. So we know we're going to have 4 zeros. I have 2 of the roots given to me. They're both imaginary, so I use my conjugates. The other root would be negative I, and the other one would be negative 2I. So if you need to, set up all of your x equals I, x equals negative I, x equals 2I, and x equals negative 2I. And then use inverse operations to get them set equal to 0. So this would be x minus I. This would be x plus I, adding I to both sides. This one would be x minus 2I, and x plus 2I. Now I just saved the 0 for the end because I'm saving some space. Following me? Yeah. And then this one's a little easier to FOIL because you don't have as much with the plus or minus. There's not like 3 things in a set of parentheses. So I would FOIL 2 of them at a time. Group them. And do the ones that look almost the same but have just the sign change, because then stuff cancels. Do not mix and match, because then it'll be a mess. So we should get x squared plus ix minus ix minus I squared. Keep that grouped. Over here we'll get x squared plus 2ix minus 2ix minus, don't forget to multiply the 2 and 2 to get 4I squared. And then you have some cancellations going on. You also know that I squared equals a negative 1. So this is minus a negative 1, which is really x squared plus 1. Over here, cancel, cancel. Plug in your negative 1. Negative 4 times a negative 1 is really plus 4. And then you would just FOIL that from there. Okay. Homework is on Google Classroom. I will go back after school and do number 12 at the end of the video. So if any of you want to watch it later. Okay, I wanted to pop back on and finish example 12 for any of you that might have been struggling. So this one is telling us that we should have a 3rd degree polynomial, which means my final answer should have x cubed in it. Rational coefficients, and the roots are negative 1 and 2 minus I. Now because this is a complex answer, we can use the imaginary root theorem and its complex conjugate, which tells me that 2 plus I is also a root. Now we work backwards to get them in linear form. So we would add 1 to both sides to get x plus 1. We will subtract 2 and add I to get x minus 2 plus I. Same thing with our last one, subtracting 2, but subtracting I. Again, make this into an equation, just so it satisfies what they asked. And then we just have a lot of distributing to do. Again, I would suggest that we start with the big ones. Lucky for us, a lot of stuff will cancel or be added together to get us a 0. So let's start. X times x is x squared. X times a negative 2 minus 2x, and x times a negative I is a minus xi. Move to your next term. We're distributing this time a negative 2. So a minus 2x. Negative 2 times a negative 2 is a positive 4. Negative 2 times a negative I would be a positive 2I. Last step is to take the I and distribute it to get me plus xi, or ix, minus 2i. We have a positive I times a negative I, which will get me a minus I squared equals 0. C will go to 0 by having inverses, so minus xi and plus xi, a plus 2i and a minus 2i. Again, every time you do this, those should go to 0 and cancel out. If not, if you still have i's, once you've simplified, you've done something wrong. So go back and look. And then don't forget, I squared is negative 1. So this is minus a negative 1, which makes a plus 1. So now we'll have x squared minus 4x plus 4 plus 1, which is plus 5. And then the very last step from there is to, of course, FOIL that and get our final answer. So we should get x cubed minus 4x squared plus 5x plus 1x squared minus 4x plus 5. And then just go ahead and collect all your like terms and put it in standard form. And that's our final answer.